Howdy, y'all, and welcome back to another lecture for ASTR 124, Introduction to Observational Techniques. I am going to be talking about the lovely subject of time. Time is of great importance to astronomers in that it helps us determine when we can actually look at things. And as we'll find out at the end of the lecture, time can also be used as the basis for a coordinate system from which other sets of motion can actually be defined. Why should we care? Well, as astronomers, as I just said, it is very important in determining when and even if an object of interest is observable at a particular time during the year. Time also allows us to measure things such as the rotation of things, how fast things rotate on their axes, how things revolve around each other, so forth and so on. And it also is very critical in time series analysis, as you might imagine. Time series analysis is the study of any phenomenon over time, such as the pulsation period of Cepheids, the decay of light from a type 1a supernovae, exoplanet transits, and on and on and on. And so we have to be very specific as to what we mean by various ways to measure time, or at least characterize time. So let's start off with solar time. Let's start off with what we all experience from day to day. You know, we have clocks on our wrist, and we have clocks, we have watches. We can tell the time basically anywhere we are. Now, where does that time come from? How do we actually measure that time? Well, we sort of naively say that that time is measured with respect to the sun. Well, kind of. There are actually two times that you can measure based on the sun, the motion of the sun. You have the true or apparent solar time, which is the time that you would measure via a sundial. If you are looking at, say, the shadow of a stick on the ground, and you marked it off at various points, with noon being where the shadow is the shortest, that would be the apparent solar time. Mean solar time, on the other hand, is what is measured by the clock. Now, the reason why the two are different is because of the fact that the Earth is tilted 23.5 degrees on its axis, which we refer to as the obliquity of the Earth, and the Earth's orbit is slightly eccentric. The eccentricity of the Earth's orbit is 0.017, if I remember correctly. And so when you compare the time on your watch to, say, the time on the sundial, you're going to see some deviations. Sometimes solar noon will occur before, or apparent solar noon will occur before, and sometimes the apparent solar noon will occur after. And so we have developed this thing called the equation of time, which is really the superposition of two sine waves. These are corrections or deviations between the two systems based on the eccentricity, which you can see in the green curve, and the obliquity of the orbit in the blue curve. And so that makes, when you add those together, you get that red equation of time. This crude diagram demonstrates the difference between true and mean solar time. And so what we're looking at is two distinct paths that the sun appears to take. You have the path that the sun actually appears to take, which is the path of the ecliptic, where the sun appears to be high up in the sky in the summer and low in the sky in the winter. And then you have the mean sun, which is effectively where the sun is if it were along the equator, the celestial equator, traveling at a uniform velocity, which is essentially the average of the sun's motion. And so if you were to project the true sun's position onto the equator from the ecliptic by just simply dropping straight down, what you would find as time progresses is that the true sun's projection will lag behind the mean sun times, and then will precede the mean sun at times, depending on whether or not it is above or below the celestial equator. LHA is the local hour angle. That is the angle in the sky at your position between the sun and local noon, or where the sun would be on the meridian, again, at that location. Now, in all of its lovely glory, this is the equation of time, where, very simply put, the equation of time, basically the difference between the mean sun and the apparent sun, is simply is A plus B. So delta T is equal to A plus B in minutes, where A is the contribution to the equation based on the eccentricity of the Earth's orbit, which you can see listed there. And then you can see B, which is the contribution to the equation of time, which is based on the obliquity of the Earth's orbit. And then you can see the lovely factors that have been determined empirically. Again, this equation of time periodically gets updated because we still even have approximations in here. The Earth's orbital period is not exactly 365.25 days. And so the equation of time, when you actually get into it, if you were looking for extremely precise time differences, then it gets rather hairy. Now let's talk about the difference between sidereal and synodic times. So sidereal time is time that is marked or referenced to a fixed star. So we make the assumption or approximation that the stars on the celestial sphere are fixed in position, meaning that given the amount of time that we are observing something, the position of that star does not change appreciably in that time. So we can use it as a fixed reference position. A sidereal rate is the true rate of that object, meaning that if you're talking about the rotation period of an object, how fast does it actually rotate about its axis, or how fast does it move from around in its orbit? That is the sidereal time. Synodic time is time marked out by the passage of the sun or the earth, depending on where you're located. If you're on the earth, then the synodic time is taken of an object in relation to the sun. If you're on the sun, then it's taken in relation to the earth. And so these times correspond to rotations and revolutions that are observed from Earth. What we see to be the change or the period of time that the moon goes through its phases would be its synodic period. This slide helps to explain why there is a difference between the sidereal time and the synodic time with relation to the Earth's orbit. Now, let's say on day one, you look up, there is the sun, and say behind it happens to be the star Vega. You then wait a day, and what you'll find is that if you could see Vega, you would see that it would be on your meridian slightly before the sun would, because the Earth, as it has moved in its orbit slightly and now needs to rotate another degree in order for the sun to be at true noon. So the synodic period of the Earth is, roughly speaking, 24 hours, but the sidereal period of the Earth, or the sidereal period of the stars, rather, is 23 hours and 56 minutes. Again, approximately. A larger discrepancy or difference between a sidereal and synodic rate is when we look at the moon. The moon has a sidereal period of 27.3 days, meaning that it rotates about its axis once every 27.3 days. However, we see the moon from the Earth go through phases. And so if we were thinking about timing the moon, or the duration from which the moon goes from, say, full moon to full moon, or in this case, new moon to new moon, that would be 29.5 days. And again, this is due to the fact that the Earth is not stationary and is moving with respect to the sun. And so as the moon is orbiting around, you have new moon is where the moon and the sun are relatively along the same line. They are in the same portion of the sky. If you wait 27.3 days, that the moon will be in the same part of the sky in reference to that background star Vega, for example. And then you have to wait another couple of days in order for the moon to rotate back into a position so that you can get that alignment of new moon where you have moon and sun back to back, or in roughly the same line. Now, if you wanted to do conversions, if you want to say you observe the synodic period of a planet, and I'll get into that in a moment, and you wanted to know what the sidereal rate was, you wanted to know how fast it actually goes around the sun. P sub sin is the synodic period of the planet. P sub sid is the sidereal period of the planet. And then P naught is the Earth's orbital period, or 365 days. So if you have the synodic period of the planet, basically the period through which it goes through a particular cycle, which again I will show momentarily, then you can very easily convert into what the true sidereal period, or how long does it take to move around the sun, again in reference to a background star. The sun, that equation has to do with what when we measure sunspots, for example. If we measure the period of the sun based on the motion of sunspots, we are actually measuring the synodic period, because again, we are moving as the sun rotates. We are moving in an orbit as the sun rotates in the same direction. And so the synodic period is going to be slightly longer than the sidereal period. And if we wanted to convert from one to the other, that is the equation that we would use. In a second, I'll go into a little bit more detail about the sun's rotation. But before I do that, let's look at those planets. So this is the Planetary Configuration Simulator. This is a wonderful tool provided by the University of Nebraska-Lincoln. They have a number of simulators in their astronomy education suite. But let's just look at the motions of the planets with respect to the Earth. This configuration is where the blue dot corresponds to the Earth and the gray dot corresponds to Mercury. And so let's start off with this configuration, which we refer to as the inferior conjunction, meaning that the Earth, Mercury, and Sun are basically in the same line. I'm neglecting inclination effects. So the synodic period is the time it takes to go from this configuration back to this configuration. So as time progresses, the Mercury is traveling along its orbit faster than the Earth is, as predicted by Newton, or as predicted by Kepler's first law of planetary motion. At this point, we can see that Mercury, with respect to the sun, is now what we call the greatest elongation. The greatest elongation is effectively the farthest away that the planet is going to appear to get from the sun. It is effectively the best time to actually observe Mercury. And you can see that it is only 23 degrees above the horizon, which is one of the reasons why I have never seen Mercury outside of it transiting the sun, because it is very low on the horizon during the sunset and sunrise. It will then move to what is known as superior conjunction. So the Mercury is on the directly opposite side of the sun. It will continue around again to greatest elongation, and then back down to the inferior conjunction. And so you can see down here that the synodic period of Mercury's orbit is 117.6 days. Again, it is how long it takes Mercury to move from a set position relative to the sun back to that same orientation. Now let's reset and talk about the sidereal rate. I have now reset the position so that we are back to the inferior conjunction where the Earth, Mercury, and the Sun are all again in the same line. And I'm going to manually move Mercury so that here you can see that this arrow points towards the reference point, or where Mercury is relative to a background star. And so I'm going to move it around, and I'm going to do this by eye, and roughly there. More specifically, it's there. What we find is you can see, hopefully you can see or imagine that there is a line passing through the Mercury and the Sun and is pointed over in this part of the sky. And that is 88.7 days. So I'm a little bit off. That is sidereal period of Mercury. So hopefully that illustrates the difference between a synodic period and the sidereal period of a planet. But you notice that there were two equations, one for inferior planets, which are planets interior to the Earth, and then an equation for superior planets, or planets that are outside. So now let's look at the situation where the planet is exterior to the Earth, or where the planet is considered a superior planet, in this case, Jupiter. And so I've started off with at opposition, where the Earth, Jupiter, and the Sun are all in line. So to be specific, you have the Sun, then you have the Earth, and then you have Jupiter on the outside. And so if I start this going, again, because of Kepler's first law, Earth is going to be moving in its orbit faster than, because of Kepler's third law, I misspoke earlier, because of Kepler's third law, the Earth is going to be moving faster in its orbit than Jupiter is. Here we have eastern elongation, or eastern quadrature. Basically, that is when as you can see here, the angle between the Sun and Jupiter is 90 degrees. Oh, as a note, opposition is when we are closest to the superior planet, and from an observational point of view, because of that, the planet is going to be bigger and brighter. So if you're interested in surface features, that's really where you want to be. This is what we call conjunction, where it's similar to the inferior conjunction that we saw before, where we have Earth on the opposite side of the Sun as the reference planet, in this case, Jupiter. And then finally, we have western quadrature. And then finally, we get to opposition again. And here you can see that the synodic period of Jupiter is 1 year, 33.6 days, meaning that if you want to see Jupiter in opposition, you really only have to wait about 1.09 years in order to see that again. So it occurs fairly rapidly. So the synodic period in this case is far shorter than the sidereal period. So let me go back to the beginning. And so the sidereal period is, if I move this around, and now Jupiter is basically pointing in that direction. And what we find is that the sidereal period, again, this is probably slightly off from the true, period. This is, again, basically by eye, just as an illustration, but the sidereal period is around 12 years. So the orbital period of Jupiter is far longer than the apparent orbit of Jupiter would imply based on its position relative to the Sun. Now let's talk about astronomical timekeeping, as it were. Because the sky is not a precise clock, the sky, the stars, the movement of such has been described as a cosmic clock. In reality, it's not a very convenient or precise clock. We have things like leap years, we have leap seconds, things of that nature. And so if you want to know how long something lasts over particularly many years or decades or even centuries, and you're looking at calendar dates, it is a little tricky to be able to calculate that. So astronomers have just simplified it. And so we just simply count the number of days. We have standardized this system called the Julian date. And the Julian date starts at 0 at the January 1st, 4713 BCE. Effectively, this is the convergence of two astronomical cycles and a tax cycle in the Roman Empire. Why it was chosen this particular way, I am not very well versed. In our textbook, it talks a little bit about it, but regardless, that's the 0 point. It is effectively arbitrary, but that is okay. So long as we all communally agree that that is in fact t equals 0 for the Julian date system, then we're all on the same page. You will probably encounter, particularly in research papers, something referred to as the modified Julian date, which is simply just a truncated Julian date. You can see that the Julian date at this point is in the millions. So since 4713 BCE, there have been roughly 2.5 million days. And since that's a pain to write down, and it's also a pain to put on graphs when you're looking at changes in time on the order of weeks or months, we just slice it down. And we basically truncate it to 24. Basically, we knock off the 2 and the 4. Incidentally, there is a canonical point at which the modified Julian date is defined, and that is actually Sputnik. So the date that Sputnik is launched is the 0 point for the modified Julian date. For myself, I just truncate it wherever I can, wherever I need to, in order to make the graphs look nice. But if you were wondering what the Julian date was on a certain date or will be in the future, the equation below will give that to you. So using my birthday, when I was born, the Julian date was 2,476 and 63 days, or a modified Julian date of 76,063 days. If you were going to put in, so Y is the target year, N is the target day within that year, and then L is the number of leap days since January 1st, 2001. If you wanted to go backwards, back before 2000, then you would put in the year as negative and the leap days as negative in order to get the right number. But at this point, in the dawn of the internet, actually getting a a calculator or a calculator conversion is really just a mouse click away. So you really don't need to do this by hand. It's just for sort of historical reasons that I'm showing you this. Now, time as a coordinate system. We can also use time as a way of defining a certain reference frame. So let's take the sun, for example. The sun is not what we call a solid body rotator. It does not rotate with the same angular velocity at all places on its surface like the Earth does. No matter where you are on the Earth, the angular rotation rate of the Earth is 2 pi radians over 23 hours and 56 minutes, basically 15 degrees per hour. But for the sun, it depends on your latitude. The equatorial regions, the gas in the equatorial regions is actually rotating faster around the sun than the polar regions by about a factor of a week or so. So at the equator, it's about 24 days. Near the poles, it's around 30 days. The person to have basically standardized the system was a guy named Robert Carrington, I think. His last name was definitely Carrington. And what he did is a bit arbitrary, but he took detailed observations of sunspots over a fairly long period of time. And what he noticed was that certain spots changed in longitude. They moved left or right in relation to the bulk motion of the sun at that position, except for certain spots that were located roughly around, if memory serves, around 26 degrees north and south solar latitude. Those sunspots seem to stay in the same line of longitude regardless of the point of rotation. And so he just set that as the Carrington rotation, or he set that as the reference rotation frame for the sun. And it has now subsequently been referred to as the Carrington rotation rate, and that is defined as 27.2753 days, or an angular velocity of 0.2303627 radians per day. So, if you're interested in the differential motion of active regions, sunspots, flages, prominences, things of that nature, if you're interested in how things move relative to each other on the sun, the easiest way to do that is to look at the sun in this rotation frame. And so you are going to base your rotation or the movement of things in relation to that 27.27 days. For example, if something is moving relative to us at a rate of, say, 29 days or 29.27 days in the frame of the sun, then that has a rotation rate or a motion or rotation rate really of 2 days. So it's simply a way to have a standardized reference frame from which to measure the position of certain features relative to other features as a function of time. And then lastly, thing I'm going to talk about is the barycentric coordinate system. Again, this is a attempt to standardize timing. So the solar system, there's a lot of moving parts, literally. We have the planets, you have asteroids, you have comets, you have the sun. All of that has a specific center of mass, and that specific center of mass is then orbiting around the galactic center. If you wanted to find a platform from which to be able to measure all times consistently so that you don't have to worry about synodic or sidereal, you would do so at the barycenter of the solar system, because that effectively does not move relative to really anything else. Everything else is moving around it. And so you don't have that ambiguity. And so you can make a coordinate system, or you can make a conversion to convert your timing that you measure of, say, the synodic period of a planet or the period of an asteroid or comet or what have you. You can convert that into the barycentric motion, and then you get basically a true rate. So you can compare apples to apples when you talk about how fast one comet is going around the sun as a function, or as opposed to another comet going around the sun. For myself, I found this to be I've used this in practice when it comes to the timing of astrophysical events, such as eclipses of binary stars, or, as I've said, the pulsation of Cepheids, because as we are moving through our orbit, because of the light travel time, we are going to see certain events, say, eclipsing events, a little bit earlier and then a little bit later. This is what one of the first measurements of the speed of light is, when a dude named Romer looked at the period of Io, because he was interested in creating some kind of universal timepiece. And he thought that the orbital period of Io would provide him that, but he noticed that depending on where the Earth was in its orbit, the period of Io changed. Sometimes it would go behind Jupiter and with a period of a certain rate, and then if you're on the other side of the orbit, Io's period would be slightly longer. So, same principle applies. If you're looking at the eclipsing binary and you look at the period, if you do so over a long enough time frame, we're talking just even months or years, definitely, you're going to notice that your pulsation or the eclipse rate changes. But that's not an astrophysical change. That is a change simply based on the motion of the Earth around the sun. And so the barycentric coordinate system was defined by the IAU, or the International Astronomical Union, in order to, again, standardize all of these timing conventions so that we can effectively compare apples to apples. All right. Well, that's it for me. I hope you found this interesting, educational, and maybe even a little entertaining. If you have any questions, please feel free to email me. And yeah, I'll see you in the next video. Peace out and clear skies.